Good morning, everyone. Today we will continue Section 4, Independent Event. We will discuss some examples to apply the definitions of independent event. And we will go through Section 5. The conditional probability is the probability. That's the topic, and we will summarize the theoretic part for chapter 3 a little quick. Then we will start chapter 4. That is the plan for today. Now let's review what is the independent event. So definitions of independent event. If the two events E and F are independent, then we call if they follow this product. Okay, yeah, I have recorded the screen. I have started. So the probability of the event E and F equals the probability of each event product. That is called event E and F are independent, and it doesn't matter you use the event letter A, B like that. There is no problem. And if E and F two events are independent, then E and F's complement, they are also independent. And we can prove that, right? We can prove that, which means we are going to prove the probability of E and F's complement equals the product of each event probability. And if we have three events, they are said to be independent. That should satisfy all those four identities, which means the intersection of three event probabilities, that will be the product of each event probability, and any two combination out of those three events, their probability should satisfy those identity. And we can extend this to more event, to, for example, the finite n event, they are independently. If we call n event, they are said to be independent, then it should satisfy any subset r less than equal to n event, they are independent. That means they satisfy this identity, right? And we have several combinations. For example, n choose n minus 1, n choose n minus 2, and until the last one will be n choose 2, right? Any two event out of those n, and we have n choose 2 different combinations, right? That is the independent for more than 3 events. And we can extend this to the infinite set of events. That is, every finite subset of those events is independent. Now let's check some examples. Okay, some examples. Example 1. An infinite sequence of independent trials is to be performed. Each trial results in a success with probability p and a failure with probability 1 minus p. What is the probability that answer those three-part questions? At least one success occurs in the first n trials. B. Exactly k successes occur in the first n trials. C. All trials result in successes. So here this kind of trial, we should be familiar with this kind of trial, okay? Because we are going to see this trial later. So we are going to see this kind of examples in chapter 4. An infinite sequence of independent trials is to be performed. It's an infinite sequence of independent trial, but we only care about the first n trials, right? In the part A and B, we only care about the first n trials, and each time, so it's like we repeat the it's not really repeat each trial, okay? It just means each trial. So each trial the probability is P. Of course, the complement event will be the trial is a failure, right? The trial is a failure will be 1 minus P. And from here, you will see that each trial, their probability for success are all P, and their probability with the failure are all 1 minus P, right? So we can define in this way, okay? We can define in this way. So let the event A, okay, we would like to write A. So let event AI means success. Let me write in this way. So we need to define the event, okay? We need to define the event. Let AI be the event. The ICE trial. The ICE trial result in a failure, okay? Result in a failure. You can also define it as the ICE trial result in a success. So let PI be the event for the ICE trial result in a failure. So the probability of the failure occurs in the ICE trial, that is 1 minus P. There is no problem, right? And we know the I can be, let me write here. The I can be 1 from n, right? The I can starting from 1 to until n. And each trial, the probability result in a failure and the result in a success, they are the same. So this probability of event AI is 1 minus P. So how about the probability AI's complement? What does AI's complement mean? That means the ICE trial result in a success, right? If it's not a failure, then it's success. From here, we can tell that, right? Either success or failure, two part, the probability. So this one will be P, right? The ICE trial result in a success. AI's complement means P, right? Means P. Then we can define another event, right? So let E let E be at least one success. At least one success occurs in the first n trials. So we are going to work out the probability of event E, right? At least one success occurs in the first n trials, which means you can have success one time, right? One time, two times, until n times, right? Then what is the complement? What does E's complement mean? So let's think about the complement of this event E. What is E's complement? At least one success, which means in n trials, you might have one success plus n minus one failure, or two success plus n minus two failures, right? Until all the n trials all result in a success, right? What is the complement for this event E? That means all the trials result in a failure, right? No success at all. Yes, very good. So all the trials result in failures. So that means we have n failures, right? Which means all the trials are failures. So that's the complement. If we are going to find the probability of event E according to the proposition, that will be 1 minus the complement of event E, right? There is no problem. Then all the trials result in a failure, and each trial is independent trial, right? Each trial is independent trial. So that means we need to find the probability all the trials are failures. So for example, so here we have n trial all failures. Let me write here. Let me write it in this way. Let's try to understand the independence here, okay? The independence here. So we have the n trials. 1, 2, 3, the i's trial, and then the n trials, okay? N trials. So the first one, the second one, the third one, and then this is the i's one. This is the last n. So all the trial results are failure, which means the first one is failure, the second one is failure, third one is failure, for the i's one is failure, and the nth one, the result are all failures, right? So what is the probability? What is the probability you get the failure so let's call it the probability, right? Probability for each trial. Let's check the probability for each trial. So in the first trial, what is the probability to get a failure? 1 minus p, right? So we said it's independent, right? It's independent trials. So whether the first one is a failure or success does not affect the second one. They are independent. So what is the probability for the second one is a failure? 1 minus p again, right? How about the ice one? The ice one is also 1 minus p, right? The nth one, the failure probability is also 1 minus n, 1 minus p. So what does this mean? All the n trials, they are all failures. That will be the product of each event probability, right? Each event probability will be all those n trials. Each one is a failure with the probability 1 minus p, right? So will be 1 minus p to the exponent n. So that will be 1 minus this all probability for each complement, which means the probability for all the trials result in a failure. All the trials result in a failure. Each one get a failure is 1 minus p. So we have n, right? We have n. Of course, it should be product, right? Should be the probability for each trial, then taking the product of those n together. So that will be 1 minus p to the exponent n. So that is the final answer, okay? That is the final answer. And for this question, okay, it will be more convenient, or it will be more clear to think about its complement, okay? Its complement, this event complement. Now let's check part B, okay? Let's check part B. Exactly case success occur in the first n trials, okay? So that means in the total n trials, there are there are k success, and then plus, so the other n minus k will be failure, right? The other n minus k will be the failure. So according to the previous one. According to part A, how can we calculate the probability for K success and N minus K failure? So the probability, okay, the probability K success and minus K failure. I haven't defined the event, okay? I haven't defined the event. If we have K success, which means for those success, those trials, we will have P times P times P, then we have K, right? We have the exponent as K. And then the N minus K trials are failures. What is the probability for the failure? So it's 1 minus P, but we have the product of N minus K failures, right? The product of N minus K failures. So that will be 1 minus P. But that is only we have K success in the N trial and N minus K failures. But let's think about this one, okay? Let's think about this one. So you might have, so this is one, this is the 1, 2 until K, and then K plus 1 until M. So you might have the first K. The first K gives a success. Let me just write S. Okay. So you might have the first K a success, or you might have the another K, right? Another K out of N trials. So you might have this is success, and all success. So the first K is success, and from K plus 1 failure until the last one is failure, right? You might have in this way, or you might have, for example, let me write in this way. Okay? Let me write in this way. You might have, for example, the first one is failure. Then starting from second one until this is K plus 1. So you still have K success, right? You still have K success until the last one, right? So you can choose which K trials out of N they have the result is a success, and the other N minus K gives a failure, right? And of course, those two, for the first N trial, those two are different outcomes, right? Are different outcomes for the independent trials. This one we call the first K gives a all success, and from K plus 1 until the N trials they are all failure. And this sequence is when the first one gives a failure, the second until K plus 1 gives success, and starting from K plus 2 until N, they all gives a failure. Of course, they are different. So how many different combinations of those sequence? So you can do in this way actually. N choose K, right? N choose K. So the probability, okay? The probability we can define the event. For example, I can define the event F. Let's work out the probability. Let if F be the event exactly K success. When you have N chooses K success, of course the others will be failure. The others N minus K will be failure. In the first N trial, trials. So the probability of this event F exactly case success occurs. We know if we, for sequence, if we have case success and n minus k failure, that will be the probability, right? That will be probability. And again here, those two are different sequence, but their probability are the same, right? For the first one, the probability is p to the k times 1 minus p and to the exponent n minus k. This one is 1 minus p times p to the k, and here we have n minus k minus 2, n minus k minus 1, then you should add this one. So the probability of those two sequences, they are the same. And actually all of those, their sequence, if we have k success and n minus k failures, their probability will be the same. But how many different combinations of those sequence? N choose k, right? When you have n choose k combinations, then the other n minus k that are all failures, the other part is just one selection. It's like times 1. Okay, this is the part for the success, and then for the failure, the other part will be failure. There is just one selection times 1, right? So that is the probability to denote part B, exactly k success. And of course, this k can be starting from 0, 1, 2 until n, right? We can have k success. K can be 0. When k is 0, which means they are all failures, right? When k is, now we can double check the answers for part A. Okay, so for example, when, let's check it. When k equals 0, when k equals 0, what is the probability for the event? So which means all the trials gives failure, right? So that will be n0 probability p to 0, 1 minus p n, right? So n choose 0 is also 1, right? N choose 0, which means you didn't choose any, right? So that is 1. It's the same like n choose n. If you follow the formula for combination, it's the same. P to the exponent 0 is also 1. 1 minus p to the m. This is the answer. This is the answer when you have n failures. 0 success occurs, which means n failures, right? So what is the probability for part A? At least one success will be the complement event for n failures. That's why we got the final answer for part A, right? For part A, because this part 1 minus p to the exponent n is the n failures, right? So that the complement event will be at least one success occurs in the first n trials, right? Now let's answer part C. Okay, part C. For part C, we can think about the first n trials. They said all trials result in success. Okay, we can consider the first n trials, and we know the n will goes to approaches infinity because this is an infinite sequence of independent trials. Consider the first n trials. Consider the first n trials. So this means all in the n trials, all the trials result in the success. So according to part B, the answer is n choose k, probability k, p to k times 1 minus p to the exponent n minus k. So this is the case. This is the case for part B. This is the case when k equals n, right? If we have n success. So it's the same. It's a case when K equals N, exactly N success occurs in the first N trials for part B, right? For part B. Now let's write it, okay? Let's write it. So the probability, you can let another event, okay? You can write let another event to keep it in a standard way. Let event G, let G be the event that all trials result in success. So that will be the probability of event G when K equals N. So that will be N choose N, P to N. So here is 1 minus P N minus N. Of course, N choose N is 1, right? N choose 1. N choose N, you only have one combination. You choose all of them together. Times P to the N times 1 minus P to the exponent 0 is also 1. So P to N. And this is straightforward, right? This is straightforward actually. All the trials are success. Each one, think about those N trials, right? Think about those N trials. So for the first, second, until the i's trial, until the nth one, it's all success, right? It's all success. Each one the probability is p, right? Each one the probability is p. So that is the product, right? That is the product of all those p. So we have the exponent is n. Now here we consider the first n trials will be p to the n, right? Will be p to the n. So we need to think about if n approaches infinity, because it's infinite trial. So that is we need to think about the limit of this one, okay? Limit of this one, and that belongs to the belongs to the limit of some sequence if my p is between 0 and 1. By the way, if probability is 0, and for those trials, okay, actually for those trials the probability p should be greater than 0, okay, should be greater than 0, and if it's always 0, then that means all the trials are always failure, right? There is nothing to discuss. So if p is a number between 0 and 1, the limit of this p to the n will give 0. If p is equals 1, of course the final answer is 1. And that is the result from the series, okay? Series. We haven't talked about this part. It can belongs to the calculus part, okay? Calculus part, how we get the final answer, because they haven't mentioned the first n trials. They just said all trials result in a success if the trial is an infinite sequence of the independent trials. That's why we write the answer in this way, okay? If the probability is 1, which means it's always success, then the limit of this series sequence is 1. If p is between 0 and 1, then the final answer is 0, okay? So that is the first example we discussed. Let's take a break, then we will continue the second examples.